Hello everyone, welcome back. In this unit, we're going to look at the topic of linear regression. And so for this unit, we're going to focus our attention on two quantitative variables. And this is known as bivariate data, where we have each individual observation that is paired with two different quantitative variables. And we're interested in exploring the relationship between these two quantitative variables. So the main focus is to create a linear model which we can use to describe and make prediction based on the observed data that we collect. All right, so we'll first start with a few definitions. So when one variable is used to predict the response of the other variable, then this is called the explanatory, or sometimes the independent or predictor variable. Now the response variable, sometimes known as the dependent or the predicted variable, is the outcome that is measured following manipulation of the explanatory variable. Okay, and so we say that these two variables are associated if changes in the explanatory variable is able to explain the changes in the response variable. So let's have a look at a few examples of identifying the explanatory and the response variables. So suppose that we have data on the circumference of oak trees as well as their age. And we want to know how old an oak tree is with a circumference of 90 centimeters. So what we're trying to predict is how old the oak tree is given their circumference. Okay, so the explanatory variable is going to be the circumference of the oak tree. The response variable, or the predicted variable, is going to be the age of the oak tree. So we want to predict the age of the oak tree based on the circumference. All right, let's have a look at the next example. So suppose we climb a mountain and measure the temperatures at certain altitudes. And we want to know the temperature based on the altitude. So we're trying to predict the temperature given the altitude along the mountain. So the explanatory variable is going to be the altitude. So that's what we're given. And we're trying to predict the temperature. And so the response variable will be the temperature. And in the last example, suppose we have the heights and the age of a high school class, and we want to know the age based on their height. So the explanatory variable is going to be the height of the students, and we're trying to predict their age. So the age of the student is going to be the response variable. Now sometimes the roles of the explanatory and response variables can be swapped, and it really depends on what we're trying to predict with what information we're given. So if we were wanting to predict the height of the students based on their age, then the explanatory variable would be the age of the student rather than the height, and the response would have been the height of the student. Now we can plot one quantitative variable versus another quantitative variable, and this is called a scatter plot. So the explanatory variable will typically go along the x-axis, and the response variable will typically go on the y-axis. So now when we're given a scatter plot, then there are four different things that we can look for. One of them is the direction of the association. So if one variable increases and we notice that the other variable will also increase, then this is called a positive association. So in the left scatter plot, what we have is the odometer reading versus the age of a car. And so we have the distance traveled by the car along the y-axis, and then the age of the car on the x-axis. So as we notice, as the age of the car increases, then the more distance the vehicle will travel, generally. So we have a positive association between the odometer reading versus the age of the car. Now, if we look in the right scatter plot, what we have is a negative association. So as one variable increases, then the other quantitative variable will decrease. So here we have the total number of births versus the literacy rate among different countries. So if we have a higher literacy rate, then we should see a decrease in the number of total births per woman. So the more educated you are, then the better decisions you will make when it comes to reproduction. Okay, so the next thing that we can look for in a scatter plot is the form of the association. So what kind of shapes do the scatter plots show? So one example here is a linear association. So if the scatter plot shows a straight line, then we have a linear association. We can also have nonlinear association. So this is an example of a quadratic association. Sometimes you might see exponential or logarithmic associations. So these are nonlinear associations. Or we can have no association. So there's really no overall pattern among the scatter plot. All right, so now the third thing that we can look for is the strength of the relationship. So if the scatter plot shows a lot of vertical spread, then we have a weak relationship. So in the left scatter plot, we have a lot of vertical distances between the points in our plot. So we have a weak relationship. So this is the example where we have the weights versus the heights of people. So there's really not a very good relationship between the weight and versus the height. And if there's very low vertical spread in the scatter plot, then we have a strong relationship. So over on the right, here we are looking at the plot of the weights versus the waist, and we have a stronger relationship because there is very little vertical spread among the data points. And now the last thing that we can look for are any unusual features. So we can look for unusual observations such as outliers that stand away from the overall pattern of the scatter plot. And we'll look at an example of how outliers can affect the strength and or direction of the relationship. So if we have a scatter plot which shows a linear relationship, so the data points fall along a straight line, then what we could do is calculate what is called a correlation coefficient. And we denote this coefficient by the lowercase r, and this will measure both the strength and the direction of the linear relationship between the two quantitative variables. So how do we calculate the correlation coefficient? Well, if we're given n paired observations, then we can use this formula to calculate the coefficient. So we're going to take the sum of zx and zy and then divide it by n minus 1. And zx and zy are going to be the standardized z-scores for each of the paired observations. So we really won't be focusing on calculating r directly, but we're going to look at using r to determine properties about the relationship. So here are some correlation properties. So if the correlation coefficient is positive, so it's bigger than 0, then the association between the two variables is going to be positive. If the correlation coefficient is a negative number, then we know that the association is going to be negative. Now, the correlation coefficient can only be a number between -1 and +1. If r is exactly -1 or +1, then all of the data points will fall exactly on a straight line. Now, the correlation will treat both x and y symmetrically, so the correlation of x and y is the same as the correlation of y and x. Now, because the correlation depends on the z-scores of the paired observations, it will have no units and are unaffected by changes in center or scale. The correlation will also measure the strength of the linear association between the two variables. So the closer the magnitude of r is to 1, so if it's very close to +1 or -1, then the stronger the linear association, and if it's closer to 0, then the weaker the linear association. And we really shouldn't be using the correlation coefficient if the relationship is not linear. Now, the correlation coefficient is sensitive to outliers, and so a single outlier can make a small correlation large or make a large correlation small. Okay, so let's have a look at some examples of the correlation coefficients. So here we have 4 different scatter plots, and these are the given correlation coefficients. So based on the correlation properties, let's match the correlation coefficient with each of these scatter plots. So if we look on the left scatter plot here, let's determine which of these 4 correlation coefficients will best fit this scatter plot. So if we notice the relationship between the points, we have a positive association. So as one variable increases, so does the other. So we know that the correlation coefficient is going to be positive. So this will eliminate R3 from the first scatter plot. Now let's also look at the strength of the relationship. The scatter plot falls almost perfectly along the straight line, so we should expect the correlation coefficient to be very close to 1. So out of the 3 correlation coefficients, the correlation coefficient that best matches the first scatter plot is going to be R4. Okay, so this correlation coefficient is going to be 0.99. Okay, so R4 describes a strong positive association. Okay, so now let's have a look at the second scatter plot. So if we look at the relationship between our variables, what we have is a negative association. So as one variable increases, the other variable decreases. And so if we look at the correlation coefficients, the only correlation coefficient that is negative is R3. And so this correlation coefficient is going to be negative 0.78. Okay, so R3 being negative 0.78 is a moderately strong negative association. And it's moderately strong since there is some vertical spread between the data points. Now for the third scatter plot, what we notice from the scatter plot is very little relationship between the points. And so out of the remaining two correlation coefficients, what we should see is that the correlation coefficient is 0.02. Okay, so it's very close to 0. So R2 being 0.02 is a very weak linear association. And so by process of elimination, this tells us that the fourth scatter plot is 0.80. So R1 describes a moderately strong positive association. And so what we notice from the scatter plot is that the association is positive. So as one variable increases, then the other variable will also increase. And there is some vertical spread between the data points. So it's not quite linear, but it's still moderately a strong relationship. So as we mentioned before, the correlation coefficient is sensitive to outliers. So we want to pay attention to any outliers as they can distort the correlation dramatically. So we have a look at the left scatter plot here. So here we have a few data points, and it shows a very strong positive association. The correlation coefficient is 0.91. Now, if we introduce an outlier to this set of data, so if we insert this data point here, then if we calculate the correlation coefficient, what we end up with is negative 0.43, which is a rather weak negative association. And so we want to make sure that we pay attention to any outliers because this can distort the correlation quite dramatically. Now there is often a confusion between the term correlation and causation. Now correlation is not the same as causation. Just because two variables are highly correlated does not necessarily mean that one variable causes the other variable. So it's tempting to say that when two variables are highly correlated, that one causes the other, but scatterplots and correlations can never demonstrate causation. At best, they can reveal an association between the two variables. There might be other hidden variables, sometimes they're called lurking variables, that may affect or change our understanding of the relationship. So let's have a look at an example of a lurking variable. So here we have the sales of sunglasses and the sales of ice cream showing a positive association between them over the summer months. So what we notice is that as the number of sales of sunglasses increases, so too does the number of ice cream sales. And so does this mean that purchasing sunglasses will cause customers to also purchase ice cream or vice versa? So what are some possible lurking variables that may be the cause of the relationship? Well, one possible lurking variable is going to be the hot weather. So on a hot summer day, the number of ice cream sales will increase due to people wanting something to cool off in the hot weather. The number of sunglasses sales would also increase due to people wanting something to protect themselves from the UV rays. Okay, so it's the hot weather that is causing both of the sales to increase, and not that one variable increases will cause the other variable to increase. So the lurking variable would be the hot weather or the high temperatures.